Today we're going to talk about simplifying radicals. And so let's just start by doing some examples. If I want to simplify root 75, I notice that 75 is not a perfect square. However, 75 is the same thing as 25 times 3, and 25 is a perfect square. We can write this as root 25 times root 3, and root 25 turns into a 5, so 5 root 3 is my final answer. So the basic idea here is we're going to be looking for perfect square factors. Ideally, you want to find the largest possible perfect square factor. So in root 200, I notice that 200 is 100 times 2, and 100 is a perfect square. Root 100 turns into a 10, and so 10 root 2 is my final answer. Now let's say you were doing this problem and instead you just noticed, well, 200 is divisible by 4, it's 4 times 50. This is okay, but you'd have to go further because 50 also has a perfect square in it. 50 is 25 times 2. Root 4 becomes 2, root 25 becomes 5, and so we end up with that exact same answer, 10 root 2. So again, it's easiest if you can find that largest possible perfect square. Now we can do the exact same thing with variable expressions. If I want to simplify root x to the 9th, I'm going to factor this as a perfect square times something else, but I'm going to have to remember that perfect squares have even exponents, so that the exponent can be divided by 2. So I'm going to factor this as x to the 8th times x to the 1. X to the 8th is my perfect square, and square root of x to the 8th, divide that exponent by 2, gives you an x to the 4th. One more example with a square root. Square root of 90b to the 10th. Let's see, 90 is divisible by 9, 9 times 10, and b to the 10th is already a perfect square because it has an even exponent. Sometimes when I have more complicated expressions, I go through and circle the perfect squares to help me remember that those are going to come outside of the radical. Root 9 is 3. Root b to the 10th is b to the 5th. I divided that exponent by 2. And the 10, which isn't circled and isn't a perfect square, stays inside that radical. Now we can do the exact same thing with cube roots, but it might be helpful to make a list of some perfect cubes, since you might be a little less familiar with those. So let's see, perfect cubes are numbers like 8, that's 2 cubed, or 3 cubed is 27, 4 times 4 times 4 is 64, 5 cubed is 125, and then variables that are perfect cubes are going to have exponents that are divisible by 3. With cube roots, you divide the exponents by 3. So 24 is 8 times 3. 8 is my perfect cube. Cube root of 8 is 2, so that comes outside of the radical, and the 3 stays inside. 250 is 125 times 2. Cube root of 125 is 5, that comes outside, and the 2 stays inside the radical. Let's see, 54 would be 27 times 2. 27 is a perfect cube, and b to the 3rd, because the exponent is divisible by 3, is also a perfect cube. Cube root of 27 is 3, cube root of b to the 3rd is b, and the 2 stays inside the radical. Now for something to be a perfect cube, the exponent has to be divisible by 3. So looking at that a to the 10th, 10 is not divisible by 3, and so then I just go down to 9. 9 is divisible by 3. So I'm going to factor a to the 10th as a to the 9 times a to the 1. b to the 12th is a perfect cube because 12 is divisible by 3. I cube root those variables by dividing the exponents by 3, and that gives me an a to the 3rd, b to the 4th, and then that a that I didn't circle stays inside the radical. It's the exact same idea with fourth roots. Let's see, 2 to the 4th is 16, and 10 is not divisible by 16, so there's nothing I can do with that 10. a to the 10th, for something to be a fourth root, we have to be able to divide the exponent by 4. 10 is not divisible by 4, and so then I'm just going to work my way down. 9 is not divisible by 4, but 8 is. So I'm going to factor a to the 10th as a to the 8th times a squared. To take the fourth root of the a to the 8th, I divide the exponent by 2, and I get a squared. And then the 10 and the other a squared stay inside the radical. All right, one more like this. X to the 12th, 12 is divisible by 4. Y to the 19th, 19 is not divisible by 4, and then you just work your way down. 18, no. 17, no. 16 is divisible by 4. So we'll factor that as y to the 16 times y to the 3rd. And we take the fourth root of the x to the 12th, y to the 16th. We get an x to the 3rd, y to the 4th. And that other y to the 3rd stays inside the radical. Now the second thing we're going to talk about today is adding and subtracting radicals. And it turns out we can only combine like radicals. It's a lot like combining like terms. If I gave you the problem 2x plus 3y plus 4x, we can only add the like terms, the 2x and the 4x, and to add them we add their coefficients. So back to example 2 part A, we can only add the radicals that are the same, and we add their coefficients. 4 root 5 plus 6 root 5 is 10 root 5, and then we've got a minus 3 root 2, which cannot be combined. Now in example B, at first glance, I don't have any like radicals at all. However, we can simplify this, and maybe we'll have some like radicals. 18 is 9 times 2, and root 9 turns into a 3. And so then I'm left with 2 times 3 times root 2, or 6 root 2. 50 is 25 times 2. Root 25 is 5. 3 times 5 is 15, so minus 15 root 2. And finally, 27 is 9 times 3, or 3 root 3. Finally, to finish the problem, I'm going to combine the like radicals, adding their coefficients. 6 root 2 minus 15 root 2 are my like radicals. 6 minus 15 is negative 9, so I'm left with negative 9 root 2 plus 3 root 3. All right, one more example. We're going to simplify the root 45 first. 45 is 9 times 5, and root 9 is 3. All of these are like radicals, so I'm going to add their coefficients. 3 minus 1 plus 3 would be 5, and so my final answer is 5 root 5. That's it for today. Let me know if you have any questions.